So stop me if you've heard this one before. The Tribonacci sequence T of n is defined as the follows. T of 0 is 0, T of 1 is 1, T of 2 is 1, and then T of n plus 3 is T of n plus n plus 1 plus n plus 2. So in other words, this is just the Fibonacci sequence, which is T of n minus 1 plus T of n minus 2, generalized to 3 numbers. Now you might be thinking this is pretty trivial. Why would Apple, Amazon, and Adobe ask this question? Well, this is not used as a actual coding challenge, but is typically used to see if you understand the very basics of data structures and algorithms. So let's just go through some examples real quick. So we know that T of 0 is 0, we know that T of 1 is 1, and we know that T of 2 is 1. So then T of 3 would be T of 0, which is 0, plus T of 1, which is 1, plus T of 2, which is 1, which would equal 2. And then T of 4 would be T of 1, which is 1, T of 2, which is 1, and then T of 3, which was 2. So this will equal 4. And then finally, T of 5 will equal T of 2, which is 1, plus T of 3, which is 2, plus T of 4, which is 4, so this will equal 6. Now you could just spit out the optimal solution to this in an interview, but they'll usually ask you to come up with a few different solutions, improving on them iteratively. Now in an interview, you could just spit out the optimal solution as fast as you want, but they'll probably ask you to take you from a suboptimal solution to the optimal solution iteratively. So let's go through that process. So the first thing we could do is just go recursively. So if we define the function, let's say Tribonacci sequence of n, we could say that if n equals 0, then just return, let's say 0, and then if n equals 1, then just return 1, and then if n equals 2, then also just return 1. So then otherwise, if it isn't one of these, then you would return, obviously just do exactly as it says. You'd return TS of n minus 3 plus TS of n minus 2 plus TS of n minus 1. So how bad is this approach? Well, if you are asked to return TS of n, then you need to return, or rather you need to calculate T of n minus 3. You need to calculate TS of n minus 2, and you need to calculate TS n minus 1. But to calculate TS of n minus 1, you need what? You need T of n minus 4, you need TS of n minus 3, and you need TS of n minus 2. And you can already see we're already starting to repeat work. So all the way over here, what we're going to have T of n minus and 4, and then you're going to have TS of n minus 5, and so on. But you can see that we're repeating T of n minus 4, and we're repeating T of n minus 4. And if you really want to go through the complexity analysis of this, you'll come out and find that it's O of, and this is really bad, 3 to the n. That's really bad. You probably couldn't even calculate, say, T of S of 36 without TLEing. So that's where the first optimization comes in, and this is a process called memoization. So the very first time that we calculate a T of S, so let's say like T of S minus n minus 3, you can save it in some sort of array. So let's say that we had our memo, and the memo goes like 0, 1, 2, 3, 4, 5, 6 all the way to n, we would go ahead and put in our base cases, which we know that 0 is 0, 1 is 1, 2 is 2. And then what would happen is when we ask it to calculate T of S n of n, it would go to n minus 3, and then down to n minus 4 and n minus 5. And it would go all the way down, and it would eventually start filling up this memo. So we would get something like this, and then that would fill up to that, and then this, and so on, all the way to n. And all the way back here, once we go back up this recursive call and go down this one, eventually we're going to get to this T of n minus 4. And we'll see that we already solved t of n minus 4 somewhere in here, let's say maybe t of n minus 4 was just 6, we've already solved it. So then we can just reference this table, return what's in this table, and we don't have to do work again. So how much of an improvement is this? Well, because you're only going to actually go down the recursive tree once for every single number, this actually improves your solution all the way to O of n, because you're only calculating each number once. However, you do have to maintain an entire memo, so now you have a space complexity of n as well. And it's also a little less optimal than it can be, because you also have to work with the recursive stack. So next we're going to look at a similar solution, but we're going to do our memoization bottom up in a process called dynamic programming. Okay, so let's assume that we've called tfs of n and we already have our base cases. So what we're going to do is we're going to initialize an array called dp, which is going to be the size up to n. So it's actually going to be n plus 1 because 0 is one of the cases. So it's 0 indexed. So we're going to start by just filling in dp of 0 as 0. We're going to fill in dp of 1 as 1 and dp of 2 is 2. And instead of recalling a recursive stack backwards, we're instead going to build this dp up. So we're basically going to loop for I equals 0 all the way to, while I is less than or equal to n, I plus plus, and we're going to calculate the dp that way. So in this case, since the Tribonacci sequence, we know that dp of I is equal basically to the previous three numbers. So it's dp of I minus 1 plus, I'm going to run out of space, dp of I minus 2 plus dp of I minus 3. So we basically do, okay, so we do 3, that's 0 plus 1, so 2. We go to 4, that's 1 plus 1 plus 2, which is 4. We go to 5, which is 1 plus 2 plus 4, which is, did I do it right? 7, right? And then 6 is going to be 6 plus 7, so hopefully I can remember some math. That's 13. Then 7 is going to be 13 plus 7, that's 20, so 24. And then 8 is going to be 37 plus 7, so 44, right? Please don't judge me for my quick math. 44 plus 24, that's going to be 68, plus 13 is going to be 70, 81. And then finally, dp of 10 is going to be 125 plus 149, so 149. So we calculate it that way. So that's dynamic programming. So again, we can look at the complexity analysis. Because we're only calculating each number once, that's going to be O of n. It's still going to be O of n space complexity because of this dp array. However, it is just going to be a slight bit faster than the top-down approach, just because we don't have that recursive stack. However, there is a way that you can optimize this further, because if you take a look, and I'll switch to a nice bright color for you, when we're calculating dp of 10, do we ever need any of these numbers, like ever again? No. dp of 10 is only going to look at dp of 9, it's only going to look at dp of 8, and it's only going to be looking at dp of 7. So what if we just eliminated the need for any of this? And in fact, we just kept the dp to size of 3. So instead of having a dp for 0, 1, 2, 3, 4, 5, 6, 7, all the way to n, we instead only kept dp of the three numbers we actually need to look at: n minus 3, n minus 2, and n minus 1. And that's what we're going to do in the optimal approach. So in the optimal approach, we're just going to keep 3 dp numbers. So that's n minus 3, n minus 2, and n minus 1. And we're going to start it off with this base case. So that's dp of 0 is 0, dp of 1 is 1, and dp of 2 is also 1. And instead of looping through every number, we're going to do this in chunks of 3. So what you can actually do is you can go from I equals 3. You can go until, and there's going to be a little caveat, but we're not going to worry about it for now. Same thing while I is less than n, and instead we're going to go up by 3 each time instead of just 1. And that means, let's say we need to calculate the Tribonacci sequence of, let's say, 6. So if I is going to start at 3, so when I is 3, we can start by saying, okay, so dp of 0, 1, 2, and 3 is going to be what? Well, n minus 3, n minus 3, or n minus 2, and n minus 1. So in fact, dp of 3 will get assigned what it needs to be. But instead, what we're actually going to do is just assign dp of 0, dp of 1, and dp of 2 just by adding up every number in here. Now, why does that work? dp of 0, adding all these numbers together, is going to change the dp array to this. 2, 1, 1. Why? Because this was dp of 0. It's going to get changed. And then dp of 1 is going to change the dp array to this, because we're not going to change dp of 0, but then 1 is going to be 2, 1, and what's already here, 1. So that's going to be what? That's going to be 4. So it actually seems like we're correctly calculating the entire dp array just by adding up all of the numbers in our 3-element array each time. So this would make it 2, 4, and 7. So then what do we need to return? Well, all you need to do is return dp of n mod 3. So if you wanted to say calculate, so let's actually do TS of 5 so we don't have to do another chunk of 3. Well, what is 5 mod 3? 5 mod 3 is 2, which means that as long as we've done enough, our answer will be right there. So then what's the complexity of this? Well, that is going to be still O of n, but then the space complexity is going to be constant. So let's go ahead and code this up. Okay, so the first thing we're going to need is our 3-element dp array, so int dp of 3, just like that. And then we need to actually fill the base cases. Now, you could do something just like this, you know, in dp of 1 equals 1. Sorry, this would be 0 and 1. But if you want to impress your interviewer, you could do something like this. You could do for int I equals 0, I is less than 3, I plus plus. You could say dp of I equals dp, or rather I is greater than 0. And why does that work? Well, that means that dp of 0 is not greater of 0, so it'll be 0. dp of 1 is greater than 0, so it'll be 1. And then dp of 2 is greater than 0, so it'll also be 1. So that's just a fancy way to do our base cases. I actually think it's more typing than normal, but people like things on one line, so whatever. Okay, so now we have to actually loop through all of the numbers. So as we said before, we're going to start at 3. If it asks us for anything less than 3, we'll just never go through this loop and return one of the base cases, so it's fine. So I is less than or equal to n. I plus equals to 3 because we're going to do chunks of 3 at a time. Now, all we have to do is do this 3 times. dp of I, or rather dp of 0 equals, well, all of the numbers. So dp 0 plus dp of 1 plus dp of 2, just like that. And then you could, if you wanted to, just copy paste like that and fix it like that. So that's good enough. But again, we can make this look a little nicer and impress your interviewers a little bit. You could just do that in a loop since they're all the same. So while j equals 0, j is less than 3, and then it's just j plus plus. So then dp of j is just equal to all of the numbers in the dp array. So then, sorry, this needs to be a semicolon. So then all we need to do, as we said before, is, sorry, this needs to be an int. We just need to do return dp of n mod 3. So is this going to work? Unfortunately not. And the reason is because this goes up to 37, which is just below the integer limit, which means that if we do this, at least in C++, it's going to crash, or rather it won't no, it'll crash at runtime. Python will allow you to do this, but we do need to set a limit such that it doesn't try to calculate any DP that will go above the integer limit. And we can actually just do that easily. We can just add a second condition for this loop such that I plus j is less than or equal to 37, which it says is the loop, the limit down here. And it guarantees us that it's going to fit within a 32-bit integer. Okay, so that is the optimal solution, sort of. Now, if you're an asshole, you could just write out all of the Tribonacci numbers all the way up to 37 and then just return them in constant time. But I bet your interviewer wouldn't let you do that.